All right, so we'll start here probably.
We will, because we're already recording.
Oh. Hello again. So we have at this point two different equations. We're getting to two different equations of motion that are looking at the time derivative of Vx and the time derivative of Vy. But we notice that they're very dependent on this Vx hat and Vy hat, and we don't really know what those are. So how can we define them? So this takes going back kind of previously to what we talked about what the velocity vector is, that it has an I hat and a j hat component. All right, so let's think about just v hat, right? So we said before that v hat essentially had an x and a y component. It's a unit vector, and how we actually define a unit vector is based on the vector itself, so in this case velocity, and we divide it through or normalize it by its magnitude.
So notice what you're doing here is all you're saying is I want a vector that points in the direction of v and it has a magnitude of 1.
Exactly.
Well, I know the vector v points in the direction of v, so if I simply divide that by its magnitude, I get a vector that points in the right direction but has a magnitude of 1.
Exactly. So then we can write it out just as we did before, because we already broke down what the vector for velocity was. It's the vx component in the I hat direction, the vy component in the j hat direction, and then its magnitude, which I'll write over here. So we get that from v squared equal to vx squared plus vy squared. So if we take the square root, that's the magnitude of the velocity vector. So now we have our v hat into two components, that vx hat, which is simply vx in the I hat direction over the square root of vx squared plus vy squared, and then our vy hat, which we get from vx j hat over the square root.
Yes, vy j hat.
Sorry, vy j hat, thank you. Vx squared plus vy squared. So now we can go back to our equation here, and we're going to be actually changing this to what we just defined. So let's write those out one more time so we have it all on one page. So we end up with the mass times the time derivative of Vx is equal to only the air resistant component. So our density times our coefficient of drag, our cross-sectional area, and now
And let's write out that v squared just explicitly in terms of vx and vy.
Yeah. So again, going back to what we just defined up here, we can change v squared, so it's vx squared plus vy squared. And now we're adding in that vx hat component. So that looks like just vx, which is what we have up here, divided by the square root of vx squared plus vy squared.
Now there's something really interesting about this that I just want to highlight. Notice that the drag in the x direction, right, in the acceleration in the x direction, actually depends on the velocity in the y direction. It is not just vx squared times vx, right? A vy appears in there. This is a pet peeve of mine. There's a vy in there. Thank you.
All right, so let's look at our y component. So now we have our mass times the time derivative of vy. That's what we're trying to figure out what that is. And now we have the gravity component added in, so minus mg. And then again, we go back to this air resistance piece. So same values. And again, we'll write out v squared as vx squared plus vy squared. And now we go up here to our vy hat, which is just equal to vy, and then divide that by vx squared plus vy squared. And I want to point out something. So why didn't I write I hat and j hat here? Well, at this point, we are looking at things just in the I hat direction, so there would actually be an I hat on this side and on this side. So we don't need to add that in this case.
Right, so we've taken that one vector differential equation, which has two components, and written each of the components separately.
Right, exactly. Cool. So do we have any other equations that are important in terms of motion?
Well, it seems like they're the sort of definitional ones that relate velocity to position.
Right. So we mentioned those previously, and we'll just write them again here. So we have the time derivative, but in this case we called it Rx is equal to Vx, and our time derivative of Ry, which is equal to Vy.
All right, so it looks to me like we have 4 differential equations here, right? 1, 2, 3, 4. And we have four sort of state variables that we're interested in, right? The x position, the y position, the x velocity, and the y velocity. So it seems like we should be able to put these into ODE45.
Right. So just to summarize all here, we have four, what you might hear people call equations of motion, and four state variables. So I'll rewrite those. So Rx, Ry, Vx, and Vy.
And why are they called state variables?
So what's really nice is they can actually give you complete information about the state of a system at a given point in time. And in this case, we're only interested in position and velocity. You can have additional state variables depending upon the system and what you're interested in, and what can actually fully define the system at that point in time, based on your coordinate system.
So one of the questions people often ask is, why isn't acceleration a state variable for this, right? And what that has to do with is the idea that position can't change instantaneously. Right, position, actually, there's sort of memory to position, right? If I'm at a given position, a little while later, I will be at some place that was related to the position I was at, right? And similarly, velocity has memory. You can't instantaneously change the velocity of something. You can instantaneously change the acceleration of something, right? I can start pushing on something and immediately have a different acceleration. So momentum is conserved, or velocity is a state variable, and also in some sense you would say position is conserved. So state variables are kind of things that are conserved. They're sort of like stocks back when we were talking about thermal systems.
Exactly. So at this point, I think we'll pause here, but think about this as your kind of first pass model that you would then go in and put into MATLAB or whatever programming software.
Well, I wonder, actually, before we do that, there's one more thing we should really emphasize, which is why this is different from the CAD problem. Because if you actually look at these equations look identical to the CAD problem, right? So why did we bother doing this problem when we already did the darn CAD problem in the reading,